Okay guys, I want to give you a quick overview of the different parameters that control the Diels-Alder reaction, which is the most important cycloaddition that we have to worry about. The Diels-Alder is always going to be a reaction between a diene, conjugated diene, and another carbon-carbon double bond that we call the dienophile. And that reaction will always happen in such a way that the diene and dienophile come together to form a six-membered ring with one double bond in it. And so if we think about how we might write a mechanism for that type of reaction, we'll start it by having the double bond of the diene reach out and grab one of the carbons of the dienophile. That will push the electrons on the dienophile back towards the diene and shift the last pi bond over. And so those three arrows can show you the new bonds that are formed during the course of the Diels-Alder. So the first arrow at the top shows the first sigma bond, the second arrow shows the second sigma bond, and the third shows the migration of the double bond that ends up in the final product. Another thing that you'll find described in your notes is how we predict regiochemistry of the Diels-Alder reaction. And so this particular Diels-Alder that I've drawn here will always come together only to give you this product where the OCH3 from the dienophile and the NO2 group from the, the OCH3 from the diene and the NO2 group from the dienophile are adjacent to one another. The way that we predict that regiochemistry is by drawing resonance structures. If you go through and draw resonance forms of the diene and the dienophile, what you'll find is that they have complementary charges at the same site so that they come together. And so I would get this resonance form from the diene where I have a negative charge on the carbon farthest away from the OCH3. I get that by drawing the resonance forms that pushes the electrons from the oxygen through the diene system onto the bottom carbon. And so that would give me this resonance form, which lets me conclude that I have this partial negative charge on the bottom carbon of the diene. If I do the same analysis with the nitroalkene, I can move the electrons in the pi system towards the positively charged nitrogen and then dump the electrons onto the oxygen. What that would give me then is a new resonance form that puts a partial positive charge onto the lower carbon of the dienophile. And then you can see that that gives me a charge matching that will dictate the fact that these two things will come together in this way. Now the final thing that I want to show you in this video deals with another term that we talked about, which is this cycloaddition happens through what's called a suprafacial addition. And what that means is that the two carbons of the diene sit down on the same pi face of the dienophile. And the reason that that has to happen is because we have to make sure that the terminal lobes on the two orbitals that are coming together match. And so on the left-hand side here, I've got the highest occupied molecular orbital of the diene, the HOMO. And if you look at that, what you'll notice is the two terminal lobes are symmetry mismatched. If I compare that to the LUMO of the dienophile, I see the same situation. The two lobes of the LUMO of the dienophile are also mismatched. But if I force the diene to come down on from the same pi face onto the dienophile, the two terminal lobes of the diene and the two lobes on the dienophile are symmetry matched to give us appropriate orbital overlap. And so that's why this reaction has to happen through that suprafacial addition.